Hello and welcome. In this video we're going to look at two more types of indeterminate forms, infinity times 0 and infinity minus infinity. Now you might look at infinity times 0 and think, how is that indeterminate? Anything times 0 is 0, right? But if you consider, these are not values that are exactly 0, they're just getting close to 0. And these are not numbers that are exactly infinity. Infinity is not really a number. It's numbers that are getting bigger and bigger and bigger in the positive direction. So consider this example. Here's a set of numbers that are getting bigger and bigger and bigger. 1, 10, 100, 1,000, 10,000. Okay, so far those numbers are getting bigger and bigger. Just multiplying by 10 to get the next number, right? Now consider these numbers. These are going to get smaller and smaller. 1, 1/10, 1/100th, 1 over 1,000, 1/10,000th. Those numbers are getting smaller and smaller. They're getting close to 0. So these are going to infinity. These are going to 0. Now if you multiply these numbers together, you get 1, 1, 1, 1, 1. It looks like when you multiply these numbers together, you get some numbers that just approach 1, right? So maybe infinity times 0 is really 1. But what would happen if, I'm going a little crazy here, I'm all by myself. What if you instead had a sequence of numbers like this? So instead of 1s, let's say you had 2, and then 2 over 10, and 2 over 100, and 2 over 1,000, and 2 over 10,000. Those numbers are still approaching 0, right? But every time we multiply these pairs of numbers, the 1 times the 2, the 10 times the 2/10, we get 2, right? So maybe infinity times 0 is 2. You can start to see why this is indeterminate. If you have a limit where one set of numbers is approaching infinity, the other set of numbers is approaching 0, and you're multiplying those pairs of numbers together, it's hard to know which one, what's happening exactly. Maybe they all multiply to 1. Maybe they all multiply to 2. You can imagine they could all multiply to 3. Maybe one of them is approaching infinity faster than the other one is approaching 0, in which case maybe they multiply to numbers that blow up to infinity. Or maybe the numbers approaching infinity are approaching infinity slower than the numbers are approaching 0, in which case maybe the product of these numbers approaches 0. You really just don't know. It's indeterminate. Infinity times 0 is an unknown limit. But we're going to be able to evaluate these limits. And the way we can do that is by a lot of times using algebra to convert a type infinity times 0 limit into a type 0 over 0 or infinity over infinity type limit. And then it's all set up to use L'Hopital's rule, right? That's exactly where L'Hopital's rule can come in and save the day. We'll look at infinity minus infinity in just a little bit. Let's focus on infinity times 0. So in example 3, we have a limit as x approaches infinity of x times sine 1 over x. And so you'll notice that the x factor, so here we have two factors. We have the x and the sine 1 over x. The x factor is approaching infinity. And then if you think about what happens to the sine 1 over x, as x approaches infinity, 1 over x is approaching 0, and sine 0 is 0. So sine 1 over x is never exactly equal to 0, but it's just getting closer and closer to 0 as x approaches infinity. So this is of type infinity times 0. It's that kind of indeterminate type of limit. So what we can do is a bit of a weird step. It seems like a strange step because it's going to make the algebra look more complicated. Right now it's nice and simplified and we're happy with it, but we're going to take this step where we're making it more complicated, but for a good reason, because we want to turn this infinity times 0 limit into either a 0 over 0 or an infinity over an infinity. So what I'm going to do is take the sine 1 over x and leave it on the top. I'm going to take the x and rewrite it as 1 over x. Now hopefully you can convince yourself that this is the same thing that we just started with. All we did was we rewrote the x as 1 over x. Not a common step, again, that you take in algebra, because it's making things more complicated. But again, for a good reason. Think about going backwards. If you divided by 1 over x, that's the same thing as multiplying by x over 1, right? Which is the same thing as multiplying by x. So these two expressions are the same. X times sine 1 over x and sine 1 over x divided by 1 over x. Those are the same expression. But now if you look at the type of this expression, the type is, well, sine 1 over x we already said was going to 0, and 1 over x, the bottom of this big fraction, 1 over x, is approaching 0 as x approaches infinity. So this now is a type of limit where we can use L'Hopital. Which means we have to take the derivative of sine of 1 over x. Now that's going to involve a chain rule because we have the 1 over x function inside of the sine function. The derivative of the outer function would be cosine. Leave the inside alone. And then we have times the derivative of the inside function. Now the derivative of 1 over x is going to be negative 1 over x squared. This is a common enough derivative that it's worth just remembering. And if you don't remember it, that's okay. You can always rederive it. Remember that you have the derivative of 1 over x can be rewritten as the derivative of x to the negative 1. That's 1 over x just rewritten using a negative exponent. And then you multiply the negative 1 in front, subtract 1 from the exponent, and you get x to the negative 2, which you can write as negative 1 over x squared. So that's the derivative of the top by the chain rule. Now the derivative of the bottom, the derivative of 1 over x, well, we just did that. That's negative 1 over x squared. Before we try to use L'Hopital again, we always want to try to simplify. Try to simplify first. And there's a lot that can simplify here. The negative 1 over x squareds cancel. And all we have left is the limit as x approaches infinity of cosine of 1 over x. Now, as x approaches infinity, 1 over x is going to approach 0, and cosine of 0 is 1. So this limit evaluates to 1. Great. So that was an infinity times 0. Now, it doesn't matter if it's positive infinity or negative infinity. It doesn't matter if you're approaching 0 from the left side or from the right side. So this works in all those cases. The same kind of idea where you take either the infinity term or factor and bring it down to the bottom of a fraction and then use L'Hopital, or bring the factor that has a 0 to the bottom of the fraction and then you get an infinity over an infinity, which then you can use L'Hopital on. Notice that for this one, we took the x, which was the thing that was approaching infinity, and as soon as we rewrote it as 1 over x on the bottom of the fraction, that 1 over infinity made it go to 0. So that made it so that we had the sine 1 over x, which was going to 0, and then we had a 1 over x on the bottom, which was going to 0 as well, so that we could use L'Hopital. So you're either taking the factor that goes to infinity and flipping it to the bottom to get a 0 over 0, or you're taking the factor that approaches 0, flipping it to the bottom to get an infinity over an infinity. Either way, you can use L'Hopital. Now, the x was the easier factor to deal with because we knew the derivative. We could figure out the derivative of 1 over x. But if we move the sine 1 over x to the bottom of the fraction by writing it as 1 over sine 1 over x, then the derivative of 1 over sine 1 over x can get kind of complicated. So you have to pick and choose what's going to be the easier one to take the derivative of. Looking at the next example, we've got the limit as x approaches 0 from the right of 1 over sine x minus 1 over x. This is a infinity minus infinity kind of limit, because as x approaches 0 from the right, sine x is approaching 0 from the right, 0 from but positive. So you have 1 over a number that's approaching 0 from the positive side, which is going to go to positive infinity. Then 1 over x, that again is the same situation. 1 over a number approaching 0 from the right, from the positive side, that's going to approach infinity. And then you have the minus sign in the middle. This is an indeterminate form because it depends on what these numbers are. The difference of these numbers could be 10. Like maybe these first numbers, the first term numbers from the first term, are always 10 bigger than the numbers from the second term, in which case the difference is always going to be 10. Or maybe the numbers that are going to infinity from the first term are always 3 less than the numbers that are going to infinity in the second term, in which case you would get -3 for your result. There's a race case between these two infinities, and we just don't know which one is going to win. So therefore, this is an indeterminate form. Well, one thing that can help us out with this limit is to put it into a single fraction. So combine these two fractions together into a single fraction, and then maybe we can use some kind of L'Hopital rule or something to help us out, like a 0 over 0. If we get that for the fraction, we can use L'Hopital or something. So let's combine these two into a single fraction, just using algebra. Get our LCD, least common denominator, and we're going to end up with x minus sine x over x sine x. All right. Now this, I don't know why I just wrote that limit first, but here the first thing you'd want to do is think about what kind of limit you have now. If you plug in 0, you end up getting 0 on the top and 0 on the bottom. So we can use L'Hopital. And hopefully that will simplify what's inside the limit. We're going to get 1 minus cosine x, our old friend from previous videos. And on the bottom, what rule are we going to have to use? If you said the product rule, that's correct. So there's the product of x and sine x. So if you're taking the derivative of the bottom, you'll do first times derivative of second plus the derivative of the first, which is 1, and then times the second, which is sine x. Now once again, let's look at what kind of a limit we have. If you plug in 0, you'll get 1 minus cosine 0, which is 1 minus 1, which is 0. If you plug in 0 to the bottom, you'll get 0 times whatever is going to be 0 there. And then, well, I shouldn't say whatever, because 0 times infinity we're talking about is indeterminate. But here you get 0 times 1, which is 0. Then you have plus 0, which is 0. So once again, we're going to be able to use L'Hopital. Here we'll get sine x on the top when we take the derivative. Then on the bottom, make a little bit more space, we're going to have the derivative of x cosine x. That'll involve a product rule. We're going to have the first times derivative of second plus the derivative of the first, which is 1, times the second. Then the derivative of sine x, that separate term, is cosine x. Now let's check to see what kind of a limit we have. If you plug in 0 into the top, you have sine 0, so we have 0 on the top. Plug in 0 on the bottom, and you've got 0 times 0, which is 0, plus 1, which means we're getting 2 on the bottom. So here, by plugging in 0, we get, here I'm going to write it out, sine 0 over 0 times negative sine 0 plus cosine 0 plus cosine 0. Whoops, where'd that theta come from? Get out of there. So we have 0 over 2, which is 0. So you want to be careful. If you had gotten a little bit too L'Hopital happy, then you would continue taking the derivatives on top and bottom, and even when you're not supposed to. Because remember, L'Hopital only works when you have 0 over 0 or infinity over infinity. So as soon as you get that 0 over 2, you're not using L'Hopital anymore. You're just taking the limit as you would at the very beginning, like earlier packets. All right, thank you for watching, and see you in the next video.